A prime use of NMR relaxation is to directly determine the wetted surface area of suspensions under relevant industrial conditions and concentrations. The most common method of particle surface area determination is BET nitrogen gas adsorption. This technique requires that the material under test be a dry powder. However, drying wet suspensions inevitably results in unintentional and unwanted aggregates and agglomerates. As a consequence, the subsequent surface area results will be skewed. Indeed, it has long been accepted that any procedure which requires a dry sample, such as BET or Knudsen flow of a gas at low pressure, may give a surface area value which, for all its accuracy, has little relation to the effective area in a liquid. Thus, it is important to recognize that a wetted surface area value from NMR relaxation measurements can be quite different from that obtained by nitrogen BET gas adsorption data, but is the more appropriate metric for suspensions. The ACON area measures suspensions directly and requires no sample pretreatment. It is inherently a much simpler measurement technique, and as little as 0.1 milliliters of sample is needed. The majority of commercial products involve suspensions of particulates in some liquid at some point in their manufacture, and typically they are concentrates. This is especially true of nanoparticulate materials. In part 1, we discussed in detail why you need to measure suspensions as they are prepared and without dilution, because otherwise it is possible to obtain a value that is not truly representative of the concentrated suspension and so may not translate into a useful performance metric. In contrast to the measurement of particle size by dynamic light scattering or light diffraction, where the raw scattered diffractive intensity data has to be deconvoluted by means of complex algorithms, sums of exponentials or Bessel functions, the relation between NMR relaxation and wetted surface area is surprisingly simple. Conversion of relaxation time to surface area is a straightforward calculation. However, as in the BET gas adsorption method, monolayer coverage of fluid onto the particle surface is assumed. Importantly, however, no assumptions are made as to the particle size and size distribution or to the particle shape, and this issue will be discussed further in a future video. So, the schematic on the left-hand side is the relaxation obtained for a 25% aqueous dispersion of a commercial polystyrene latex of nominal particle size 100 nanometers. The relaxation time was determined to be 40.2 milliseconds, which translates to an average suspension surface area of 59.1 meters squared per gram. Since the latex particles are spherical, we can calculate the surface area based on the nominal particle size of 100 nanometers, and this computes to 57.1 meters squared per gram. Although the results are in good agreement, the lower latter measured value arises because the suspension is not truly monodisperse and almost certainly is not a uniform size distribution. In this case, the choice of a mean, modal or median size will result in a different calculated surface area. This issue will be examined further in a future video. The table on the left shows data for a series of batches of a commercial bihydrol polyurethane latex. These materials are low volatile organic compounds used for coatings applications from automotive to medical usage. According to supplied technical literature, the solids concentration is 40% and the samples were each measured as received. From the table, it can be seen that two of the batches are clearly different. Batch number 694 has a lower surface area at 30 square meters per gram, while batch number 888 has a larger surface area at 36 meters squared per gram. They could potentially be out of specification.